our first speaker of the session will be Wim Wiertz from Gpixel. You can correct your name then. And Wim will give us a talk about latest developments in high throughput CMOS image sensors. So Wim, stage is yours.
Thank you. Just push this on for the next, I guess. Okay, thank you. So good morning, everyone. First of all, thank you for the organization, for having us, obviously. So I'm from Gpixel, and the topic of today is to give you an overview on the latest developments we are doing on high throughput or high speed image sensors. Very quickly about Gpixel, I think most of you know us. We make image sensors. We do that for various applications, but typically our main business focus is industrial imaging, so like this world, obviously. And we do that both for custom and standard off-the-shelf products, but standard products are really our prime focus. But first of all, as I said, we talk about high speed. The question is always, of course, what is high speed? You have different people having a different opinion about that. So I try to define it today here for all of you. So, of course, our customers make cameras, and cameras output their data with interfaces. So speed definition typically in this industry is tied to the camera interfaces. And for the purpose of this presentation, I kind of defined high speed, everything which is more than 10 gigabits per second. We have today I think more and more coming up popular is the 5 GHz interface as kind of mainstream interface. So everything which is faster than that, I guess, is what we see as high speed or the industry. There is a lot of CXP12 interfaces coming up. We have like Immersion with their nice high speed GHz interfaces. So that's kind of the definition from our point of view. So if you then talk about different products and technologies, I'll try to mix both of them a little bit. So the first product example I have is one of our line scan sensors. This is, if you talk about sensor technology, this is just kind of plain what we call front-side illumination, wafer fabrication technology. So this is kind of old school, sort of say. So this is what we call an 8K line scan sensor. So 8K refers to the horizontal resolution with 7 micrometer. But if you then look to the throughput from a sensor point of view, you see that we do roughly about 31 gigabits per second total throughput, data throughput of the sensor. So if you then talk about interfaces, you have some overhead, so it kind of increases a little bit. So you talk about all in all an interface speed of like 40 gigabits per second in those kind of products. So typically for application point of view, it's like high-speed inspection. Recently, kind of a booming application in the industry is like EV battery inspection. So that's requiring, of course, that goes on kind of a conveyor belt, so that goes quite high speed. So that's where these sensors actually find their place. We also have a live demo at our booth, if you're interested. This is the first product. Again, this is kind of older school technology. What we recently developed as well is TDI line scan sensors. And that's actually going one step further in terms of throughput. For those who are less familiar, TDI is also a line scan technology, but actually where you move on the sensor, you push actually the acquisition over different lines. And the reason why to do it is to basically for low light conditions that you can sum exposure at exposure, so that even in light starving condition, you actually still have a decent image. Can be light starving condition or can also be very fast throughput. Of course, the shorter your exposure time, the less light you have, so it's not always high speed, but can also be very, it's not only low light, but can also be very high speed. The solution we developed here is kind of moving from a front-side illumination technology to a backside illumination technology. If you do that, you have a little bit more flexibility in terms of sensor architecture. You can route the signals a little bit more efficiently. So if you then look from a specification point of view, you see here that we reach a throughput of up to 74.3 gigabits per second from a sensor point of view. So this is already, I would say, one step further in terms of throughput. In terms of resolution, in this case, it's a little bit different. As I said, it's TDI technology. So of course, we also talk about the horizontal resolution. But here in this case, you have the lines that you move one after another. So you have, in this case, 9K horizontal resolution, but also like 256 stages that we have. This is kind of the number of cumulations that you can do before you output the signal to your output interface. In this particular case, we have not one, but two arrays. So we have 256 and 32 stages. The reason for doing that is to create high dynamic range imaging. So you have your sum either 32 or 256 times your signal of the same object line. And the 32 output data is then used for very bright parts of the scenes. 256 cumulations are then used for dim part of the scenes. So this is really for what we call higher end applications. So it's more going into high-end flat panel display inspection, PCB inspections, and so on. TDI is also used a lot for aerial imaging, which is kind of less the focus of this this industry, of course. So as I said, we have the BSI technology, so backside illumination, that next to being, for us, making it easier for the high speed throughput, also enables higher QE and possibly opens also different wavelengths. So it's also more sensitive to UV wavelengths, for instance. So that's one step we are taking. Then the next step we have taken recently actually is with a product family called G-Sprint. G-Sprint is still what we call then front-side illumination technology, but with a very advanced readout. So here we kind of pulled all the tricks out of our box in terms of how to, as fast as possible, do the readout. In this particular case, we have typically you read out the sensor from top to bottom, line by line. In this case, we read from 4 sides. So we have essentially 4 quadrants in the sensor to really boost up the frame rates. So that enables, as you can see, up to 192 gigabits per second total data rate. So people always ask us, why do you go so fast? Because we don't have interfaces that can live with that. But typically those sensors survive for like 10, 15 years. So our goal is always to do it faster than the interfaces, and then typically the industry catches up. We have seen that in the past, and it will probably happen again. But these are actually, this is a nice product. We have, of course, we have different resolution versions for different applications. The nice thing here too is that we can, for the high-speed industry, we have a pixel where we can do binning. So the pixel size is 4.5 micrometer, but we can do real charge domain binning. So it's like a CCD binning where we sum the full well. So you have a much higher full well, and you also quadruple the frame rate. So the frame rates that you see here are for full resolution readouts. So if you do binning, it goes ×4. Also, if you reduce certain region of interest, it goes even faster. So also for this sensor, we have a live demo. So if you would be interested, feel free to come and see. These are like for the 3 members, the detailed specifications. So as you can see, we have, of course, high throughput also means a lot of interface lanes. So in this particular case, and also the previous products, this is still kind of old school LVDS interfaces. So that is still preferred for a lot of customers. I will talk about high-speed serial interfaces a little bit too. But for these kind of products, this is still interfaces. So okay, I think more interesting part is this is what we have done up to now. But what's next? So obviously we keep on developing, keep on doing things. And this is kind of a slide that I would like to show just to, maybe not all of you are familiar with how sensors are made, but this is kind of how the innovation has been done for an image sensor technology. So on the drawing on the left side, you see what we call a front-side illuminated sensor. So this is the classic way how people make chips, basically. So you have on top, your light comes in, you have typically like small micro lenses per pixel, you have optionally a color filter, and then the light has to go to a grid of metal to go down to the photodiode where the light is captured and the signal is converted to electrons. Now, obviously, that's not ideal. You can see that. You have to do tricks to funnel the light in the right way. Also, of course, the more circuitry you add on top, the harder it becomes for the light to go through. So one evolution that has happened over the years is to switch to backside illumination. So there you essentially flip the wafers or flip the orientation of the photodiodes and the wiring. And there you can actually then, your photodiode is on top. So you can have much more complex metal connections inside your pixel without jeopardizing your light sensitivity. So that has been an important evolution where we are taking use of. Of course, it also comes with challenges. For people who are familiar, if you have a global shutter sensor, you need to store the image inside your pixel. With a front-side illumination sensor, it's a little bit easier. So your memory node, you want to shield that from light. With a front-side illumination sensor, it's easy. You just put metal on top, and it's relatively shielded. With backside illumination, you can see it becomes harder because the metal is under the photodiode. So there you need to do a lot of special tricks together with the wafer foundry to still have some shielding. So that becomes a little bit more challenging in combination with global shutter. Next generation is what we called wafer stacking. So that becomes even more interesting. Then you basically combine backside illumination, but you stack that with a second wafer. There are different techniques to do that. The first generations were only stacking on the sides. What we do now is what we call in-pixel hibit stacking. So we can basically connect every pixel to the second wafer below that. And that really opens up literally a new dimension for us, because we have a second wafer where we can have like purely a digital wafer, where we can have memory, where we can have very short connections. So of course also like on a PCB, we have RC limitations on a sensor. So with stacking, we can really overcome that. So we have been implementing this in different sensors. This is one example where we made a sensor for the video industry. So it's a full frame optical format, what they call 8K resolution. So it's 49 megapixel total resolution with 8K horizontal resolution. And what we have done here, as you can see kind of schematically on the top left, is we have two layers, as I explained. We have the pixel layer on top, and the second layer has all the ADC converters, but we also have a full-sized image SRAM memory on it. So we use that for various things. We use that for high-speed readout, but we can also add exposures. So in a pixel, for instance, you have your full well, which is limiting. If you can add different exposures, you can partially overcome your full well limitation. This is a product we have released end of last year, so that's the G-Cine product, already using stacking technology. Then, very shortly to give an outlook, we are of course also taking that BSI stacking technology to a next level. So we are working on new sensors where we are pushing the limits even further. So there you talk about truly high speed, even more high speed. You talk about, as you can see here, tens of thousands frames per second, so up to 42 gigapixel per second, or crazy bit rates of more than 800 gigabits per second. So obviously that there the interfaces for sure are not ready for, but these are then more first generations are going into cameras with like in-camera memory, so they can store it before they transfer it. But just this is an example where, yeah, this technology really enables us to go for crazy high speeds. Huh? Of course, it comes with other challenges. You need to get the data of the chip. So in this case, we have like 164 high-speed serial interfaces, so it becomes also challenging on the FPGA side. So conclusions, just to give you an overview. From a technology point of view, there have been a lot of evolutions. I think today we are really, we need to go to BSI, wafer level stacking, to take the next step. But it's really an interesting step because it really opens up different dimensions. We can really go to things which we only dreamed of the past 20 years. So it's a lot of fun for us. It's kind of a new toolbox that opens up. So we are still very eager to make new sensors. We have new possibilities. So it really enables us to come up with novel ideas together with our customers and partners to solve problems and add things. So it's still exciting time for us to do new things. So we have a booth here. If you want, feel free to step by. Thank you.
Thank you very much. Thank you very much for the nice presentation. Thank you for the overview about your technologies and especially to give this outlook on the latest developments. Or the next gen outlook. There's room for questions. Are there any questions? Okay. I have a question, actually. On one slide, you mentioned a CCD in CMOS. What's behind that?
Well, that refers to the fact in the old CCD technologies, you were basically moving electrons, which has pros and cons. In CMOS, what we typically do is we convert electrons to voltage in the pixel. But that makes it harder really to sum electrons, noise-free, basically. So for those advanced TDI technologies, we actually had to go back to CCD technologies together with the wafer foundry, so that we can, in an easy, noise-free way, still move electrons, add electrons, and then at the end convert it again to digital, to voltage and then digital. So it's kind of making the best of both worlds, actually. Using the CCD feature where it was ideal for, and then all the rest using CMOS technology for the high speed and the implementation on chip. So it's it needs flexibility from the wafer foundry because you're combining two technologies. But luckily we have nice suppliers that are willing to join our journey on this. So. Okay,
another question from online.
Okay, there you go.
They ask, can you have timing info, or what's about timing information? Is it understandable?
Not really, no. Maybe timing on next generations, or on to the last slide, or
maybe timing info when the next gen is come to the market. Let's interpret it like that.
Yes, yeah. Well, the products I showed are already on the market.
They're
if we talk about the latest slide, basically, these are products that we are doing now. Some of them are OEM. We are also looking for standard products. So we talk about 2-3 years before we have quite a long cycle in product development. So basically, everything that you see is developed 3 years ago. So what I'm showing now will be on the market in 2-3 years from now.
Okay.
So it's still, you need to have still some patience, but I think we can, it's coming.
The online question got a little bit more precised. Can you have timing info on the arrival of photons?
The arrival of photons. It's,
okay.
it's the speed of light, right? That kind of hits the silicon, but
I don't know. We have to. Sorry about that, but we cannot interpret these short questions which come up here from online. Sorry about that. Okay. Thanks, Wim. Thanks for the presentation.
Thank you.